Welcome. Today I'm going to talk to you guys about error and error analysis. We're going to go through this very quick, so it shouldn't be too rough for you. Uh, Error, unfortunately, even for somebody as awesome as myself, is something we can't get rid of in science. It's something that we sort of have to embrace the fact that there's going to be error. That said, there are ways to be able to minimize that error. But the first step with any problem is recognizing that there is a problem. And so when I run up against student work that is just wildly wrong, wildly incorrect, my first thought is, did these students not understand how to analyze the error that they had in their system? Why are they asking me about it? They should know how to analyze error. And that's what we're going to talk about today. So you have a pretty good sense. If you've done anything like this in chemistry or in any of your other science classes, it should be a review. If not, because physics tends to be a little bit more math heavy than some of the other sciences, you may not have done it this way before. So we're going to go ahead and take a look at it here. To do that, I'm going to slide myself off to the side, and I'm going to formally welcome you to Error Analysis. That's video 006. In our sequence, it's the last one for the first unit. So hopefully this has been a good first unit for you, and hopefully you've gotten into the system of using the videos for your advantage. All right, with that said, we're going to go on to the next slide here. So my question for you is, what if my data are not perfectly on the best fit curve? So you guys have now had a chance to do some data analysis, some data collection, and then graphing analysis. So you should be familiar with our scatter plots, which is something that we do in the class all the time. And so let's imagine that we have a data set that looks something like this, something along those lines. You can easily tell from that data set that there is a relationship between the x variable and the y variable. And by that I mean the one that's on the x axis and the one that's on the y. Just as a side note, don't ever forget that almost always in physics we put the independent variable on this axis and the dependent variable on that axis, unless there's a very good reason for not doing that. And if there is a very good reason for not doing that, I will be sure to let you know before we get too far into it. So my question for you is, what is the relationship here? Well, as we saw in the previous video, we have a relationship that looks like that, and it looks pretty linear. Obviously I didn't draw that a perfect line, but that's okay. So you can see that that best fit line, it kind of goes through the center of the data points, but it doesn't actually hit all of the data points. And no, not all of the data points are actually on the line. In fact, very few of them are on the line. So my question for you is, why? Why does that happen? Why does it always happen? It's always going to be that way. Now, physicists do error analysis in a very mathematical way. We're not going to do that mathematical way of analyzing our error. But we are going to make sure that you recognize where the error is primarily located in this in all of your experiments. For an actual physicist, what they would do instead of writing a data point like that is that they would likely do a data point and then put error bars around the data point like so, saying that the actual value of the measurement lies somewhere between this line and that line, but this was the value that we actually got. This error right here, these error kind of margins of error, if you will, the plus or minus a certain percentage, usually comes from the experimental techniques. So it comes from the techniques or the tools, one of the two. Excuse me. However, there are other types of error that might have accounted for the fact that these are off, and so let's take a look at those here real quick. So obviously you can't get rid of all of it. All physicists end up using data points like something like this, where you have a recognized and acceptable amount of error in your measurements. However, if you don't recognize where all of your error is, then it's hard to get rid of the stuff that you can get rid of. So this stuff, can't get rid of it, but there are ways to get rid of some of the other stuff. And so that's what we're going to take a look at here. Excuse me. Okay, so, oops, there we go. Okay, so this first type of error is the easiest to recognize, although it's the one that I think most people in this class somewhat, they don't really see it sometimes unless they are very good at the mathematical analysis at the end, and that, of course, is human error. It's the easiest to get rid of, if we're honest. Human error is how I like to think of it as how your partner messes up your work. So if you were to come along and say you had a length of 12.3 meters and you had another length of 1.4 meters and you were supposed to find the total length, and your partner, because it's never you, your partner adds those two numbers together and ends up with 12.7 meters, that's human error. You know, that's one of those things where maybe you typed it into the calculator wrong, maybe you tried to do it in your head and did it wrong. Those are problems, and those are problems that are easy to fix because you can go back to your data and do the calculations correctly. One of the other areas for human error, so first we have calculations, right? So calculations is a big source. And then the other method or the other problem that you might run into is if you come up with, let's say, a measurement tool like so, and the measurement tool has markings on it, like so. Oops, that's all right. You get the idea. And you try to measure out your object like that, and you just misread it. So human error could be misuse of the tools. So those are the two big areas where where you might have some problems. It's always important if you have a measurement tool that you're not familiar with or your partner's not familiar with that you ask or you do some research before you start your analysis, your observation gathering. It's critical because you put in a lot of work on these experiments, and for you to get to the end and have done everything right except using the measurement tools, there's no way to fix that. This method right here, calculations, you can go ahead and easily fix your calculations because you know that you made the observations correctly. This, you've got to do that whole experiment again, and nobody wants to do that. So please make sure that you know how to use the measurement tools correctly. This is the one that is the most critical. So again, ask if you have problems. Don't hesitate. Just ask. It's okay. Literally everyone in the room, including myself, at one point had to ask how to use certain measurement tools, even if they seemed obvious. It's totally okay. There's no judging there. Okay? All right. The second type of error is a little bit harder to get rid of, but it's easier to recognize, I think, and that's systematic error. So systematic error is something where your device itself messes up your work. So first one, human error, you had your partner messing up your work. Systematic error is when your device messes up your work. So let me give you an example of this. This is where, if you've seen the video on accuracy versus precision, this is where you would see somebody with let's say, a bow and arrow that had a systematic error. Wow, that was terrible. I'm going to go ahead and erase that. See if I can do it a little bit better here. So you've got a target like so, and somebody comes along with a bow and arrow and hits an arrow here, 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 and here. Okay. Now that grouping is very tight. So my guess is that they had systematic error. So what was the problem? The problem was not the person. The problem was the bow itself. So this is where the device causes problems. And usually, just like with a bow, the device is not calibrated correctly. So it's a calibration issue. Usually that's the case. Let's say you're using a triple beam balance and your partner forgets to zero it. Sounds like that's human error, But in reality, because every measurement you make based on that measurement device, that triple beam balance, is off by the same amount, it's because of the calibration or the lack of calibration that you have error. Everything's going to be off by the same amount. So it's a systematic error. It's always off the same way. So it's easier to recognize, I think. The problem with systematic error, of course, is that once you've made all your observations, you recognize that you have this problem with your observations. The only way to fix it, really, is to go back and do it again. You could make a calculation where you could say, rather than calibrating the device, you could say, well, it looks like every time I'm off by this much with my bow and this much, and so I can aim that much farther down. So I'm going to go ahead, instead of aiming right at the target, I'm going to aim that much farther down and see if I can hit, because my arrows should end up this far over and that far up. So I could take that into account by doing some calculations. But really the best way for this class is to retake your observations, unfortunately. Hopefully that makes sense. The main thing to take away from this is always, always, always check your calibration before you go ahead and do your measurements. It's just the way that it is. Now, there is one other thing to take into account, and that is sometimes you may want to alter the technique that you use to be able to take those measurements. So there's another way to do it, and it's not as good. Typically, you'd want to try to check your calibration. Okay, last slide. Here we go. So random error, and random error is the one that is the hardest to get rid of. So let's imagine for a moment that you are trying to drop a coin onto a target. So here's the floor, like so, and you've got a target drawn out on the floor, like that, and you have a coin, which looks like this, that you're trying to drop onto that target. And you want to drop it from a certain height here and get it to land on that target. Now the problem with this is that there are a lot of variables that you can't control for. For example, even minuscule changes in the angle of the coin that you can't observe are going to have an effect on where the coin ends up. You could also, if you're doing multiple coins, you could end up having coins with slightly different compositions. Very, very slightly different compositions that may not even be measurable on your triple beam balance, but are measurable in the fact that they affect the way that the coin bounces or the way that it lands. You could have dings in the coin itself. You could have, it could be slightly misshapen or slightly thinner or all sorts of other things that you just can't measure. So this is just based on the randomness of the universe. Unfortunately, it is the way that it is. It's built into the universe itself. Now, we can try to get rid of as much as possible, and we do that by controlling as many variables as we can. So control your variables. I don't know why my pen is acting a little strange, but control your variables. Why do you want to control your variables? Because those random errors can be minimized if you can take as many variables as possible and make them as constant as possible. It doesn't get rid of all of it, but it does get rid of some of it. Now, as I said before, this randomness is actually a fundamental part of the universe. A guy named Werner Heisenberg told us in his theory that there is a certain uncertainty that you cannot get rid of when you're trying to make measurements. Typically, that uncertainty is for exceptionally small objects like electrons. However, from a philosophical standpoint, it's important to remember that his point is a valid one, that your observations are going to be as good as you can make them, but they're never going to be perfect because of, in part, because of this randomness. It is just the way that it is. And so it's a part of all experiments. And that's why at the beginning of the slides set, I said that In the end, when they graph data points, physicists tend to do error bars around their data points so that they can let you know that this randomness was controlled as much as possible, but there's still a range of values over which the actual measurement is probably located somewhere in there. Hopefully that makes sense. Okay, so error is important to remember. If you get to the college level, they're going to make you do error analysis measurements and calculations, but we're not going to have you do that. So you're welcome. All right, so I wanted to thank you guys for watching. Don't forget to fill out those note sheets. Note sheets should be pretty straightforward for this, and question forms. If you have any questions, again, that's it's going to drive our discussions the next day. So again, thanks for watching. It's one of those, error is one of those things that is actually kind of liberating. So just keep that in mind as you're doing your experiments. If you come up to me and ask me if you did it correctly, I can say if you did it well, but there is no real correctness in physics because of this error that's built into the entire universe. So do it as well as you can, but don't worry too much if you're a little inaccurate or if you have a little bit of error, because everyone does. It's totally okay. Thanks for watching. Have a great day.